In geometry, curvilinear coordinates are a coordinate system for Euclidean space in which the coordinate lines may be curved. These coordinates may be derived from a set of Cartesian coordinates by using a transformation that is locally invertible at each point. This means that one can convert a point given in a Cartesian coordinate system to its curvilinear coordinates and back. The name curvilinear coordinates, coined by the French mathematician Lamy, derives from the fact that the coordinate surfaces of the curvilinear systems are curved. Well-known examples of curvilinear coordinate systems in three-dimensional Euclidean space are Cartesian, cylindrical and spherical polar coordinates. A Cartesian coordinate surface in this space is a plane. For example, z equals 0 defines the xy plane. In the same space, the coordinate surface r equals 1 in spherical polar coordinates is the surface of a unit sphere, which is curved. The formalism of curvilinear coordinates provides a unified and general description of the standard coordinate systems. Curvilinear coordinates are often used to define the location or distribution of physical quantities which may be, for example, scalars, vectors, or tensors. Mathematical expressions involving these quantities in vector calculus and tensor analysis can be transformed from one coordinate system to another, according to transformation rules for scalars, vectors, and tensors. Such expressions then become valid for any curvilinear coordinate system. Depending on the application, a curvilinear coordinate system may be simpler to use than the Cartesian coordinate system. For instance, a physical problem with spherical symmetry defined in R3 is usually easier to solve in spherical polar coordinates than in Cartesian coordinates. Equations with boundary conditions that follow coordinate surfaces for a particular curvilinear coordinate system may be easier to solve in that system. One would, for instance, describe the motion of a particle in a rectangular box in Cartesian coordinates, whereas one would prefer spherical coordinates for a particle in a sphere. Spherical coordinates are one of the most used curvilinear coordinate systems in such fields as earth sciences, cartography, and physics, and engineering. Orthogonal curvilinear coordinates in 3D coordinates, basis, and vectors. For now, consider 3D space. A point P in 3D space can be defined using Cartesian coordinates, equivalently written, or in another system, as shown in Fig. 1. The latter is a curvilinear coordinate system, and are the curvilinear coordinates of the point P. The surfaces Q1 equals constant, Q2 equals constant, Q3 equals constant are called the coordinate surfaces, and the space curves formed by their intersection in pairs are called the coordinate curves. The coordinate axes are determined by the tangents to the coordinate curves at the intersection of three surfaces. They are not in general fixed directions in space, which happens to be the case for simple Cartesian coordinates. A basis whose vectors change their direction and/or magnitude from point to point is called local basis. All bases associated with curvilinear coordinates are necessarily local. Basis vectors that are the same at all points are global bases, and can be associated only with linear or affine coordinate systems. The relation between the coordinates is given by the invertible transformation functions. The point P can be written as a position vector r in Cartesian coordinates, where x, y, z are the coordinates of the position vector with respect to the standard basis vectors x, a, e, z. Note: for this article E is reserved for the standard basis and B is for the curvilinear basis. However, in a general curvilinear system, there may well not be any natural global basis vectors. Instead, we note that in the Cartesian system, the standard basis vectors can be derived from the derivative of the location of point P with respect to the local coordinate. We can apply the same derivatives to the curvilinear system locally at point P to determine a system of basis vectors specific to location P. We define these may not have unit length, and may also not be orthogonal. In the case that they are orthogonal at all points where the derivatives are well defined, we define the Lamé coefficients by and the curvilinear orthonormal basis vectors by. It is important to note that these basis vectors may well depend upon the position of P. It is therefore necessary that they are not assumed to be constant over a region. In general, curvilinear coordinates allow the generality of basis vectors not all mutually perpendicular to each other, and not required to be of unit length. They can be of arbitrary magnitude and direction. The use of an orthogonal basis makes vector manipulations simpler than for non-orthogonal. However, some areas of physics and engineering, particularly fluid mechanics and continuum mechanics, require non-orthogonal bases to describe deformations and fluid transport to account for complicated directional dependencies of physical quantities. A discussion of the general case appears later on this page. Vector calculus differential elements. Since the total differential change in R is so scale factors that they can also be written for each component if R. However, this designation is very rarely used, largely replaced with the components of the metric tensor GIK. Covariant and contravariant bases, spatial gradients, distances, time derivatives and scale factors are interrelated within a coordinate system by two groups of basis vectors that are locally tangent to their associated coordinate path line, which transforms like covariant vectors, or basis vectors that are locally normal to the isosurface created by the other coordinates, which transforms like contravariant vectors, is the del operator. Consequently, a general curvilinear coordinate system has two sets of basis vectors for every point. B1, B2, B3 is a covariant basis, and B1, B2, B3 is the contravariant basis. The covariant and contravariant basis vectors types have identical direction for orthogonal curvilinear coordinate systems, but as usual have inverted units with respect to each other. Note the following important equality, wherein denotes the generalized Kronecker delta. A vector V can be specified in terms either basis, i.e., using the Einstein summation convention. The basis vectors relate to the components by and where G is the metric tensor. A vector can be specified with covariant coordinates or contravariant coordinates. From the above vector sums, it can be seen that contravariant coordinates are associated with covariant basis vectors, and covariant coordinates are associated with contravariant basis vectors. A key feature of the representation of vectors and tensors in terms of indexed components and basis vectors is invariance, in the sense that vector components which transform in a covariant manner are paired with basis vectors that transform in a contravariant manner. Covariant basis. Constructing a covariant basis in one dimension. Consider the one-dimensional curve shown in Fig. 3. At point P, taken as an origin, x is one of the Cartesian coordinates, and q1 is one of the curvilinear coordinates. The local basis vector is b1 and it is built on the q1 axis, which is a tangent to that coordinate line at the point P. The axis q1 and thus the vector b1 form an angle alpha with the Cartesian x-axis and the Cartesian basis vector e1. It can be seen from triangle PAB that where e1, b1 are the magnitudes of the two basis vectors, i.e., the scalar intercepts pb and par. Note that par is also the projection of b1 on the x-axis. By increasing the distance from P, the angle between the curved line q1 and Cartesian axis x increasingly deviates from alpha. At the distance pb, the true angle is that which the tangent at point C forms with the x-axis, and the latter angle is clearly different from alpha. The The angles that the q1 line and that axis form with the x-axis become closer in value the closer one moves towards point P and become exactly equal. At P, let point E be located very close to P, so close that the distance P is infinitesimally small. Then P measured on the q1 axis almost coincides with P measured on the q1 line. At the same time, the ratio P becomes almost exactly equal to cos alpha. Let the infinitesimally small intercepts PD and P be labeled, respectively, as dx and dq1. Then, thus, the directional cosines can be substituted in transformations with the more exact ratios between infinitesimally small coordinate intercepts. It follows that the component of B1 on the x-axis is, if Chi equals Chi and Chi equals shear smooth functions, the transformation ratios can be written as an. That is, those ratios are partial derivatives of coordinates belonging to one system with respect to coordinates belonging to the other system. Constructing a covariant basis in 3 dimensions doing the same for the coordinates in the other 2 dimensions, B1 can be expressed as. Similar equations hold for B2 and B3 so that the standard basis, E1, E2, E3, is transformed to a local basis, B1, B2, B3, by the following system of equations. By analogous reasoning, one can obtain the inverse transformation from local basis to standard basis. Jacobian of the transformation. The above systems of linear equations can be written in matrix form using the Einstein summation convention as. This coefficient matrix of the linear system is the Jacobian matrix of the transformation. These are the equations that can be used to transform a Cartesian basis into a curvilinear basis, and vice versa. In 3 dimensions, the expanded forms of these matrices are in the inverse transformation. The unknowns are the curvilinear basis vectors. For any specific location there can only exist one and only one set of basis vectors. This condition is satisfied if and only if the equation system has a single solution. From linear algebra, a linear equation system has a single solution only if the determinant of its system matrix is non-zero, which shows the rationale behind the above requirement concerning the inverse Jacobian determinant. Generalization to n dimensions. The formalism extends to any finite dimension as follows. Consider the real Euclidean n-dimensional space, that is Rn equals R times R times R, where R is the set of real numbers and times denotes the Cartesian product, which is a vector space. The coordinates of this space can be denoted by x equals. Since this is a vector, it can be written as where E1 equals, E2 equals, E3 equals, n equals is the standard basis set of vectors for the space Rn, and I equals 1, 2, n is an index labeling components. Each vector has exactly one component in each dimension and they are mutually orthogonal and normalized. More generally, we can define basis vectors by so that they depend on q equals, i.e., they change from point to point. Bi equals bi, in which case to define the same point x in terms of this alternative basis, the coordinates with respect to this basis vi also necessarily depend on x also, that is vi equals vi. Then a vector v in this space, with respect to these alternative coordinates and basis vectors, can be expanded as a linear combination in this basis. The vector sum that describes V in the new basis is composed of different vectors, although the sum itself remains the same. Transformation of coordinates from a more general and abstract perspective. A curvilinear coordinate system is simply a coordinate patch on the differentiable manifold n that is diffeomorphic to the Cartesian coordinate patch on the manifold. Note that 2 diffeomorphic coordinate patches on a differential manifold need not overlap differentiably. With this simple definition of a curvilinear coordinate system, all the results that follow below are simply applications of standard theorems in differential topology. The transformation functions are such that there's a one-to-one relationship between points in their old and new coordinates, that is, those functions are bijections, and fulfill the following requirements within the domains. They are smooth functions. Chi equals chi. The inverse Jacobian determinant is not zero, meaning the transformation is invertible. Xi. According to the inverse function theorem, the condition that the Jacobian determinant is not zero reflects the fact that three surfaces from different families intersect in one and only one point and thus determine the position of this point in a unique way. Vector and tensor algebra in three-dimensional curvilinear coordinates. Note: the Einstein summation convention of summing on repeated indices is used below. Elementary vector and tensor algebra in curvilinear coordinates is used in some of the older scientific literature in mechanics and physics and can be indispensable to understanding work from the early and mid-1900s. For example, the text by Green and Zerner. Some useful relations in the algebra of vectors and second-order tensors in curvilinear coordinates are given in this section. The notation and contents are primarily from Ogden, Nagdi, Simmons, Green and Zerner, Baser and Weikert, and Charlotte. Tensors in curvilinear coordinates. A second-order tensor can be expressed as where denotes the tensor product. The components Sij are called the contravariant components, Cj the mixed right covariant components, Cj the mixed left covariant components, and Sij the covariant components of the second-order tensor. The components of the second-order tensor are related by the metric tensor in orthogonal curvilinear coordinates at each point. One can construct a small line element dx. So the square of the length of the line element is the scalar product dx and is called the metric of the space, given by indices can be raised and lowered by the metric relation to Lamé coefficients. Defining the scale factors hi gives a relation between the metric tensor and the Lamé coefficients. Note also that where hij are the Lamé coefficients. For an orthogonal basis we also have, example, polar coordinates. If we consider polar coordinates for R2, note that are the curvilinear coordinates, and the Jacobian determinant of the transformation is R. The orthogonal basis vectors are Br equals, B theta equals. The scale factors are R equals 1 and H theta equals R. The fundamental tensor is G11 equals 1, G22 equals R2, G12 equals G21 equals 0. The alternating tensor in an orthonormal right-handed basis. The third-order alternating tensor is defined as in a general curvilinear basis. The same tensor may be expressed as it can also be shown that Christoffel symbols of the first kind where the comma denotes the partial derivative. To express gamma ijk in terms of gij, we note that since using these to rearrange the above relations gives Christoffel symbols of the second kind, this implies that other relations that follow are vector operations. Product. The scalar product of two vectors in curvilinear coordinates is cross product. The cross product of two vectors is given by where is the permutation symbol and is a Cartesian basis vector. In curvilinear coordinates, the equivalent expression is where is the third-order alternating tensor. Vector and tensor calculus in three-dimensional curvilinear coordinates. Note: the Einstein summation convention of summing on repeated indices is used below. Adjustments need to be made in the calculation of line, surface and volume integrals. For simplicity, the following restricts to 3 dimensions and orthogonal curvilinear coordinates. However, the same arguments apply for n-dimensional spaces. When the coordinate system is not orthogonal, there are some additional terms in the expressions. Simmons, in his book on tensor analysis, quotes Albert Einstein saying the magic of this theory will hardly fail to impose itself on anybody who has truly understood it. It represents a genuine triumph of the method of absolute differential calculus, founded by Gauss, Riemann, Ricci, and Levi Civita. Vector and tensor calculus. In general, curvilinear coordinates is used in tensor analysis on four-dimensional curvilinear manifolds in general relativity, in the mechanics of curved shells, in examining the invariance properties of Maxwell's equations, which has been of interest in metamaterials and in many other fields. Some useful relations in the calculus of vectors and second-order tensors in curvilinear coordinates are given in this section. The notation and contents are primarily from Ogden, Simmons, Green and Zerner, Baser and Wycott, and Charlotte. Let phi equals phi be a well-defined scalar field and v equals v a well-defined vector field, and lambda 1, lambda 2. be parameters of the coordinates geometric elements tangent vector. If X parametrizes a curve C in Cartesian coordinates, then as a tangent vector to C in curvilinear coordinates, using the definition of the Lamé coefficients, and that for the metric Gij equals 0 when Ij, the magnitude is tangent plane element. If X parametrizes a surface S in Cartesian coordinates, then the following cross product of tangent vectors is a normal vector to S with the magnitude of infinitesimal plane element in curvilinear coordinates, using the above result, where is the permutation symbol, in determinant form. Integration differentiation. The expressions for the gradient, divergence, and Laplacian can be directly extended to n dimensions. However, the curl is only defined in 3D. The vector field phi is tangent to the cheek coordinate curve and forms a natural basis at each point on the curve. This basis, as discussed at the beginning of this article, is also called the covariant curvilinear basis. We can also define a reciprocal basis, or contravariant curvilinear basis, by all the algebraic relations between the basis vectors, as discussed in the section on tensor algebra. Apply for the natural basis and its reciprocal at each point x.